Welcome to the API 571 Audio Masterclass series. This episode is brought to you by Mag Integrity. For the complete high-resolution study guides, API 571 exam prep question banks, and to unlock our full private audio library, visit our premium engineering portal at magintegrity.ca.
Usually when we talk about a diagnosis, whether you're dealing with like a medical issue or an engineering failure, there's this baseline expectation of precision.
Right, you expect a clear answer.
Yeah, exactly. It feels binary. Like if you break your arm, the x-ray shows that jagged white line on the black film, and the doctor just points at it.
And says, there it is.
Right. It's clean, it's visual, and honestly, it's kind of comforting. I mean, we fundamentally like our problems to be visible. We want to point at them.
Oh, absolutely. We want the problem right there on the surface so we can, put a patch on it, weld it, or just replace it.
Yeah.
Human beings are just visual creatures. If we can't see the degradation, our default assumption is often that, well, everything must be structurally sound. But then you step into the world of high-temperature metallurgy.
Which changes everything.
It really does. You walk into a refinery, and suddenly that comforting X-ray machine is, well, it's completely useless.
Muddy waters.
Totally. We're looking at a diagnostic landscape that is entirely murky. I mean, imagine standing in front of a massive, heavy-duty industrial-fired heater tube.
Roaring away.
Right. And it looks perfectly fine on the outside. In fact, you put an ultrasonic thickness gauge on it, it might even measure at its exact original manufactured thickness.
But inside.
Exactly. Inside, the very atomic structure of that solid metal has been fundamentally rewritten. It is the absolute definition of diagnostic muddy waters.
It's basically an invisible chemical invasion.
Yeah.
And it's a mechanism that operates entirely silently, completely out of sight, until you're literally on the brink of a catastrophic, brittle failure.
So today, we are taking a deep dive into our source material to explore this highly insidious damage mechanism known as carburization.
It's a critical one.
It really is. Because if you're an inspector or a process engineer or an operator listening to this, understanding this specific mechanism is vital. It forces you to rethink what solid steel actually means.
Right, because it's not what you think it is.
Exactly. We are going to thoroughly decode the metallurgical theory behind this, pinpoint the exact materials that are susceptible.
And map out those operational drivers.
Yes, and finally figure out how on earth you hunt down a microscopic threat out in the field.
Well, to truly grasp carburization, we have to kind of throw away the idea that a piece of steel is just this static, dead lump of metal.
Right, we have to zoom all the way in.
Exactly, right down to the microscopic level. Because at the microstructural level, steel is essentially a matrix.
Like a grid?
Yeah, a carefully engineered solid solution of iron, a little bit of carbon, and depending on the specific alloy grade, various other alloying elements like chromium or molybdenum.
Right, and in its healthy manufactured state, this matrix is structured and it's strong. And importantly, depending on the alloy, it's ductile.
Which is key.
Yeah, meaning it has the ability to flex, to absorb kinetic energy, and to yield slightly under pressure without, just snapping in half.
Precisely. The atoms in that lattice are actually arranged in a way that allows them to sort of slip past one another slightly when they're put under stress.
But carburization destroys that.
It completely destroys that arrangement. So at elevated temperatures, when this steel is in contact with a carbonaceous material or a carburizing environment, carbon from the outside environment actually physically absorbs and diffuses into the solid metal.
Okay, let's unpack this diffusion concept, because I think it's the biggest hurdle for people to get their heads around.
It is counterintuitive.
Yeah, because we're not talking about a pipe acting like a filter with holes in it. We are talking about solid metal. How does carbon actually get inside solid metal?
So think of the iron atoms forming a rigid three-dimensional grid, or a lattice.
Okay, a grid.
At room temperature, that grid is tight, but when you introduce immense heat, the atoms in that grid start vibrating wildly.
Because of the thermal energy.
Exactly, and the spaces between the iron atoms literally expand. Now, the carbon atoms out in the high-temperature gas are significantly smaller than the iron atoms.
Oh, I see.
Yeah, so because the grid has expanded, those tiny carbon atoms can literally squeeze into the microscopic gaps between the iron atoms and migrate deeper and deeper into the solid wall of the pipe.
Okay, so if I'm picturing this right, let's use a sponge analogy.
I like a good analogy.
If the healthy steel is a normal, flexible kitchen sponge, the carbon out in the process fluid is, like, dirty water.
Okay.
You put the sponge in the water, and the dirty water slowly permeates all the way through to the center.
It's a good starting point for visualization, but here is where we have to refine that analogy.
Oh, why is that?
Because the carbon doesn't just sit in those gaps like water in a sponge. It actually chemically reacts.
Oh, reacts?
Yeah, carbon on its own is a relatively soft element. I mean, think of graphite or soot.
Right. Very soft.
But when this external carbon diffuses into the solid molecular structure of the hot steel, it has a massive chemical affinity for the defensive elements inside that steel matrix.
So it's not just a passive absorption.
Mm.
It is an active chemical attack from the inside out.
Exactly. The invading carbon chemically binds with elements like iron and, very specifically, chromium to form complex molecules called metal carbides.
Metal carbides, okay.
And these metal carbides are entirely different beasts from the original metal. They are incredibly hard, and critically, they are severely brittle.
Wow.
They're essentially microscopic, ceramic-like structures forming inside the metal matrix.
Okay, so to update my sponge analogy, the dirty water soaks into the flexible sponge, but the moment it gets inside, it reacts with the sponge material itself.
Right.
And every pore that absorbs the water physically crystallizes and becomes glass-like.
That's a much better way to look at it.
So you still have the exact same outward shape of a sponge, and it still weighs about the same, but if you try to bend it or squeeze it, it doesn't flex anymore. It just shatters into shards.
That is exactly what is happening. The outer layer of the pipe has literally turned to a glass-like matrix, while the inner layers, the ones closer to the outside air, might still be unaffected.
For now, at least.
Right, for now. Because as the process continues, that brittle, glass-like layer just grows deeper and deeper into the wall thickness of the equipment.
Now, there's a phrase in the metallurgical data from our source that really caught my eye. It says that the formation of these carbides depletes the surrounding matrix.
Yes, that's a crucial point.
I want to make sure we make this crystal clear for the listener. What exactly is the steel being robbed of? I mean, is it just losing its physical flexibility?
No, it's much worse than that. It is losing its chemical defense system.
Its defense system.
Yeah.
Yeah.
If we look at how advanced steel defends itself, we look at elements like chromium. In a stainless steel, chromium is, well, it's the absolute superstar.
The heavy lifter.
Exactly. It's the essential element that gives the metal its legendary corrosion resistance and high-temperature oxidation resistance. It acts as the shield. But carbon absolutely loves chromium. When the carbon enters the material, it forcefully pulls the chromium out of the solid solution to form those brittle chromium carbides we just talked about.
Wait, so the chromium is still physically inside the pipe, right?
Physically, yes.
But because it's now locked hands with the carbon to form this brittle carbide molecule, it can no longer do its original job.
Precisely. Because the chromium is now locked up in these new brittle structures, it is no longer freely available in the surrounding metal matrix to fight off corrosion or oxidation.
Oh, wow.
The steel is literally being robbed of its defensive shield at the microscopic level. The surrounding matrix becomes chemically impoverished.
So it is a brutal double-edged sword. You're gaining these brittle, glass-like carbide inclusions that ruin your mechanical strength, and simultaneously, you are losing your chemical shield, making the metal highly susceptible to other forms of attack.
Exactly right.
The data highlights the physical consequences of this microstructural degradation very clearly. It states that carburized steel becomes severely brittle, it may spall or crack, and it actively reduces and can completely eliminate the remaining sound metal wall thickness.
And that phrase right there, sound metal wall thickness, that is the absolute nightmare for an inspector.
Why is that?
Because it means that even if you measure the physical pipe wall and it's still a beefy, say, half-inch thick, the portion of that wall that has been carburized, maybe a quarter of an inch deep, can no longer be relied upon.
It's structurally dead weight.
Exactly. It cannot hold pressure safely. It cannot resist thermal shock. It's just dead weight.
Which brings up a terrifying operational thought for you out there. If this carbon soaking process is so deeply destructive and entirely invisible from the outside, the immediate question anyone running a plant has to ask is my specific equipment vulnerable to this?
Which means we need to look at the materials.
Right. And the metallurgical data here is remarkably uncompromising. It provides a highly specific list of susceptible materials and alloy limitations.
And it basically covers everything.
Yeah, it really does.
There is very little room to hide when it comes to material selection here. The source data lists almost every standard high-temperature alloy at risk.
Give us a list.
We are looking at standard carbon steel. We are looking at low alloy steels.
Right.
Then we move up the ladder to the 300 series stainless steels, the 400 series stainless steels, and it explicitly includes cast stainless steels as well.
I want to pause and define those for anyone listening who might not be a metallurgist by trade, because understanding why they are all susceptible is key.
That's a good idea.
So carbon steel is exactly what it sounds like, an alloy consisting primarily of iron with a small amount of carbon without any fancy intentional alloying elements.
Very basic.
Right. Then low alloy steels have additions like, up to 9% chromium and maybe some molybdenum for high temperature strength. These are your standard chromoly steels that you see everywhere in a refinery.
Correct. Those are the foundational building blocks of the plant.
And then we get to the expensive stuff, the stainless steels. The 300 series are austenitic, meaning they have a face-centered cubic crystallographic structure.
Let's give them a visual for that.
Okay, to visualize that, imagine stacking oranges in a grocery store display. A face-centered cubic structure is a very specific, tightly packed way of stacking those iron and chromium atoms, which makes the metal incredibly tough and completely non-magnetic.
That is a great way to picture it.
Thanks. Then you have the 400 series, which can be ferritic or martensitic. They stack their oranges differently, making them magnetic and giving them different thermal properties.
But here's the kicker.
Yeah, according to the data, regardless of how you stack the atoms, all of them, carbon steel, chromoly, 300 series, 400 series, are susceptible to carburization.
And the list does not stop at standard stainless steel. The data highlights specific high alloy vulnerabilities that are absolutely critical to note.
We're talking about the really exotic stuff now, right?
Exactly. Highly specialized exotic metallurgy. The source specifically lists nickel-based alloys that contain a significant iron content.
Does it name specific ones?
Yes, it exacting points to alloys 600 and 800. It also names HK and HP alloys.
What are those used for?
Those are specialized cast austenitic stainless steels used in the absolute most extreme radiant heat sections of a furnace.
Okay, I have to push back on this because it feels counterintuitive to standard engineering logic.
How so?
Usually in corrosion engineering, if you have a problem with carbon steel, you upgrade to stainless.
Oh.
If stainless fails, you upgrade to a high nickel alloy like alloy 800. You just keep throwing money and better chemistry at the problem until it goes away.
That is the standard playbook, yes.
So why isn't there a single silver bullet alloy here? Why does a super expensive nickel-based alloy still fail?
That is the critical realization every engineer has to make when dealing with these high-temperature environments. Think about it. What do all of the materials on that list have in common? From the cheapest carbon steel pipe to the most expensive cast tube.
Well, they're all metals.
They all contain iron. And almost all of them contain carbide-forming elements like chromium, molybdenum, or niobium.
Wait, so the very elements that give them their strength are their Achilles heel.
Exactly. Carburization does not care how expensive the alloy is or what its fancy trade name is. It only cares about the atomic chemistry.
Oh, yeah.
If there are elements within that matrix that the carbon can bind with to form metal carbides, the mechanism will proceed.
So the iron is really the problem here.
Yes. The data specifically emphasizes that for those expensive nickel-based alloys, a significant iron content is the critical threshold that invites the damage. Iron is the gateway.
So if there's enough iron mixed into that nickel alloy, the carbon will find it.
It will. It will diffuse into the lattice and start forming those destructive carbides.
So basically, if the metal relies on iron or carbide-forming elements to hold itself together, it has a built-in vulnerability. The carbon is literally just floating around, waiting for the right conditions to strike.
That is exactly right. If we connect this to the bigger picture, since virtually no standard structural refinery metal is entirely immune by its very chemical nature, it becomes obvious that the real trigger for this damage isn't just the metal itself.
Right, because my stainless steel kitchen sink isn't turning to glass.
Exactly. The metal provides the fuel, but the intense operational environment it lives in provides the match.
So we need to map out the critical operational variables and drivers, the things that allow this microscopic chemical invasion to actually get underway.
Precisely. The environment is everything here.
The source data outlines 3 conditions that absolutely must be satisfied simultaneously for carburization to occur. It's basically the recipe for a metallurgical disaster.
Let's hear them.
Condition 1, exposure to a carburizing environment or carbonaceous material. Condition 2, a temperature high enough to allow diffusion. And condition 3, a susceptible material, which we just established covers almost everything with iron in it.
Let us really drill down into that second condition, the temperature threshold,
Okay.
because this is the absolute golden rule for anyone monitoring operating windows or furnace temperatures. The metallurgical data explicitly provides the exact temperature threshold.
What is the magic number?
The process typically requires metal temperatures above 1,100 degrees Fahrenheit. That is 595 degrees Celsius.
1,100 degrees Fahrenheit. I want you to really internalize how hot that is. That's not just a warm summer day. That is extreme, glowing red, radiant heat.
It's blistering.
That is the kind of heat where you can feel it on your face from 30 feet away. So what happens below that temperature? If I'm running my process at, say, 900 degrees Fahrenheit, does the carbon just bounce off the pipe?
Essentially, yes. This goes back to our earlier discussion about the atomic grid.
The lattice.
Right. At lower temperatures, even at a scorching 900 degrees, the atomic structure of the steel is still relatively tightly packed, and the kinetic energy of the carbon atoms in the gas is simply too low.
They just don't have the energy to push in.
Exactly. The carbon simply cannot force its way into the solid metal matrix. But once the skin of that metal crosses that specific 1,100 degree Fahrenheit threshold, the atomic lattice of the steel physically expands and vibrates with such intense energy that the atomic doors are essentially thrown wide open.
And the carbon just rushes in.
Yeah, the tiny carbon atoms can now literally slip between the iron atoms and diffuse deep into the core of the material.
Okay, so the doors are open, but what exactly is waiting outside to get in? What is providing all this carbon in the first place?
The process fluid itself.
Right. The data extracts very specific environmental drivers. It says carburization favors a high gas phase carbon activity, and it explicitly lists the culprits.
And they are.
Hydrocarbons, coke, gases rich in carbon monoxide, carbon dioxide, methane, which the source also lists as CH4 and ethane.
In a refinery, you are practically swimming in those compounds every single day.
Yeah, you really can't avoid them.
But what is truly fascinating about the data here is not just what must be present to cause the damage, but what must be absent.
Oh, this is a really interesting point.
It highlights a strict absence requirement. For this rapid, destructive carburization to occur, the environment must have a low oxygen potential.
Really?
It explicitly states there must be minimal oxygen or steam present in the gas phase.
You know, that feels like another paradox to me. Usually, we think of oxygen as the enemy. Oxygen causes rust, oxidation, scaling. Why is the lack of oxygen suddenly so dangerous here?
Because we have to understand what good rust is.
Good rust.
Yes. Oxygen, when it's present, actually reacts with the chromium or iron in the steel to form a thin, highly protective, stable oxide scale on the surface of the metal.
Think of it like a microscopic chain-link fence forming right on the skin of the metal.
Exactly. That oxide scale acts as both a chemical and a physical barrier. The gaps in that oxide fence are incredibly way too tight for the carbon atoms to slip through.
So it physically blocks them.
It blocks the carbon from ever reaching the bare iron matrix below. But in a highly reducing environment, meaning a chemical environment packed with hydrocarbons and virtually no oxygen, that protective oxide scale either never forms in the first place or it actually gets chemically stripped away.
Leaving the bare metal matrix completely naked and exposed to the high carbon gases.
Exactly. No oxygen means no oxide shield. No shield at 1,100 degrees Fahrenheit means the carbon rushes right through the open doors of the lattice.
So we have the bare metal, we are operating above 1,100 degrees, and the pipe is filled with high carbon gas. Let's talk about the speed of this invasion. Does it happen overnight?
Not quite overnight, no.
The source data details the time at temperature kinetics. It says that carbon initially diffuses into the component at a very high rate, which then tapers off as the depth of carburization increases into the wall.
This is a classic diffusion kinetic curve, and it's crucial to understand why this tapering occurs.
Walk us through it.
Imagine the exact moment a perfectly clean, brand new, bare steel tube is exposed to this high heat, high carbon gas. The concentration gradient is massive.
Because it's all carbon on the outside and none on the inside.
Right. You have 100% carbon activity on the outside pushing against the metal and 0% carbon inside the fresh steel matrix. And nature abhors a vacuum, so the carbon rushes into the surface layer of the metal incredibly fast.
Like the dry sponge soaking up the water as fast as it can.
Yes. But as that outer microscopic layer of the steel absorbs the carbon and forms all those dense metal carbides we talked about earlier, it reaches a state of matrix saturation.
The sponge gets totally full. It literally cannot hold another drop.
Precisely. The outer surface becomes completely saturated with carbon. Now, for the new carbon atoms out in the gas stream to reach the deeper, unaffected layers of the stale wall, they have to navigate and push their way through that already saturated, highly congested outer layer of thick carbides.
Oh, I see.
Yeah, so that saturated outer layer begins to act as a slight bottleneck, physically slowing down the overall rate of diffusion deeper into the tube wall.
So the deeper it goes, the harder it is for the carbon to keep traveling. But, from an engineering standpoint, that's cold comfort.
Very cold comfort.
Because even if the rate of deepening slows down, the damage is already done to that outer layer.
Exactly. The rate might taper off, but by the time it does, the outer wall is already compromised, severely brittle, and structurally useless. You have lost your sound metal thickness regardless of the slowing kinetics.
But wait, we are talking about steady-state operations here, just running the plant day in and day out. But the data specifically calls out critical process events that takes a slow, creeping diffusion and throw it into absolute overdrive.
Yes, the process events are the real danger zones.
It details that steam and air decoke cycles are highly dangerous. Why? Because temperatures during these decoke cycles often exceed normal operating temperatures, massively accelerating the carburization.
It's true.
Here's where it gets really interesting. And honestly, the irony of this specific operation is just staggering to me.
It is a profound operational paradox, and it is exactly where a lot of plants unknowingly destroy their own equipment. We really need to walk through exactly why an operator decides to run a steam or air decoke cycle in the first place.
Right. Let's look at the operator's control screen. They are running a furnace. Over time, the hydrocarbons flowing through the tubes start to thermally crack.
They break down.
Yeah, and they lay down a layer of solid carbon coke on the inside wall of the pipe. Now, that coke acts like a thermal blanket.
Which is bad for heat transfer.
Exactly. It insulates the inside of the tube, meaning the operator has to fire the furnace harder and hotter on the outside just to get the same amount of heat into the process fluid on the inside.
Right. They are wasting fuel, the efficiency drops, and the tube metal itself gets dangerously hot. So the operator decides it is time to clean the tube.
Makes sense.
They take the unit offline from normal production, and they run a decoke cycle. Their goal is to intentionally burn off and remove that solid coke buildup from the inner diameter of the tube.
So they are actively trying to rid the system of carbon. They are fighting the fouling.
Yes, they are trying to do the right thing. But to physically ignite and burn off that solid coke, they have to introduce air or steam, and crucially, they have to raise the temperature of the furnace.
Uh-oh.
Often, they have to push the furnace well beyond its normal, safe operating temperature just to get the dense coke to ignite and clear out of the system.
And there's the trap.
That is the trap. If that massive temperature spike pushes the actual metal of the tube significantly over that 1100-degree Fahrenheit threshold, consider what is happening at the microscopic level.
The atomic doors swing wide open.
Exactly. And what is sitting directly against the bare metal?
A thick, solid layer of pure carbon coke.
Yes. You are effectively baking the carbon permanently into the atomic matrix of the steel in your desperate attempt to get rid of the carbon on the surface.
Wow. That is wild. So you managed to burn the coke off the surface, you clean the tube, your heat transfer improves, and you're sitting there thinking you've done a great job.
You think the unit is fresh and clean?
But in the process, you have completely destroyed the underlying metallurgical integrity of the wall. You win the battle against fouling, but you completely lose the war for asset integrity. That is a brutal trade-off.
It is, and it happens far more often than people realize, simply because the damage is completely invisible during the decoke cycle itself.
So now that you, the listener, understand this perfect storm of extreme heat, high carbon gas, the absence of an oxygen shield, and the massive risks associated with routine decoke cycles, we really need to map exactly where this storm occurs inside a complex refinery.
Let's look at the refinery impact and the affected equipment.
Right. The metallurgical data is very precise about the primary victims of this mechanism. It does not list 20 different types of equipment. It identifies the most common culprit without hesitation.
Fired heater tubes.
Fired heater tubes, the absolute fiery heart of the refinery. And it lists the specific process units where these tubes live. We are talking about heater tubes in catalytic reformers and coker units, or really any fired heaters where coke can form on the inside of the pipes.
And it specifies the furnace types, too.
It does. It specifically names ethylene pyrolysis furnaces and steam reformer furnaces.
If we look closely at why these specific massive units are the primary victims, it all perfectly aligns with our three critical variables.
Heat, carbon and susceptible metal.
Right. Catalytic reformers, cokers, ethylene pyrolysis furnaces, and steam reformers, these are not your standard low-temperature boilers.
Not at all.
These are the absolute workhorses of high-temperature, aggressive chemistry. They operate at the extreme upper limits of standard metallurgy, often running well over the 1100-degree Fahrenheit threshold as their normal everyday baseline.
And what is flowing through them? Pure, concentrated hydrocarbons. They're literally swimming in the exact high-carbon gases that drive the carburization kinetics.
Just massive volumes of it.
I want you to really visualize the inside of a fired heater tube in one of these units. It is not just some warm liquid gently flowing through a household plumbing pipe. It is a high-pressure, ultra-hot, violent, roaring environment.
And the data highlights a very specific, localized risk within these turbulent tubes. It states that the coke deposits themselves act as a direct physical source of carbon that promotes localized carburization.
We touched on this during the decoke cycle discussion, but let's expand on it a bit. The coke is not just a thermal insulator. It's an active chemical antagonist.
Exactly. When a solid lump of coke deposits and latches onto the inner wall of that roaring heater tube, it is essentially pure, concentrated carbon in direct, intimate physical contact with the hot steel matrix.
Just pressed right up against it.
Yeah. You do not even need the gas phase carbon floating by at that point. The solid coke is acting like a high-pressure carbon injection system right at the surface of the metal, driven deep into the lattice by the intense radiant heat coming from the firebox on the outside of the tube.
Which means the metal directly underneath that specific lump of coke is going to carburize and turn brittle much faster than the clean, unfouled sections of the tube right next to it.
You get a hot spot of damage.
Right, you're getting localized, highly concentrated degradation.
Precisely. It creates a severely weakened, brittle spot in a tube that is already operating under extreme internal pressure and extreme thermal stress. It is a ticking time bomb.
Which leads us to the most critical operational question in this entire analysis. If these tubes are slowly turning to brittle glass inside these massive roaring furnaces, and the actual damage is happening completely out of sight at the microscopic atomic level, how on earth does an inspector actually spot the damage before the tube violently ruptures and causes a major incident?
This is where it gets tough.
We need to talk about in situ inspection and damage detection.
The source data provides a comprehensive breakdown of the field cues, but I must warn you, this is where the reality of carburization becomes quite grim. Because by the time many of these visual cues appear to an inspector on a walkdown, the damage is already in its advanced critical stages.
Oh, so it's almost too late.
Usually, yes. The source explains the visual and dimensional field cues of severe damage: bulges, heavy scale, thin line, brittle cracking, and what it specifically calls thick lip tube failures.
It also mentions that the cracking can manifest in a distinct crow's feet appearance. Let's talk about the thick lip failure, because the physics behind that is just fascinating.
It's a very specific signature.
Normally, when a standard, healthy metal tube fails from overpressure or general thinning, it balloons out, right? The internal pressure pushes against the weakening wall, the metal stretches, it balloons, and eventually the edges of the rupture tear and stretch until they are razor thin. We call that a thin lip failure.
Exactly. A thin lip rupture indicates ductile failure. It is what steel is supposed to do. The metal yielded, it absorbed energy, and it stretched until it physically could not stretch anymore.
But remember what has happened to our carburized steel?
It can't stretch.
Right. It is no longer a flexible matrix. It is a glass-like network of chromium and iron carbides. It has lost all its ductility. It cannot stretch even a fraction of a millimeter.
So when it finally gives way under the massive internal pressure of the process fluid, it doesn't balloon, it just snaps.
Like glass.
It snaps violently, and because it did not thin out or stretch before snapping, the edges of the resulting rupture remain at their full original thickness.
The thick lip.
That is the classic thick lip failure. If an inspector walks into a firebox after a failure and sees a rupture with thick, blocky, unstretched edges, it is the immediate hallmark of a catastrophic brittle fracture, most likely driven by extreme carburization.
The data details a specific phenomenon that drives this catastrophic snapping. It details what it calls catastrophic carburization.
Which is a terrifying phrase.
It really is. It states that in advanced stages, the metal undergoes a volumetric increase. The forming carbides cause the surrounding metal to literally crumble due to this increase in volume, resulting in significant metal loss over time.
This comes down to pure physics and crystallography. We discussed earlier how the tiny carbon atoms slip into the lattice and bond with the chromium.
Right.
Well, when you take the original iron and chromium atoms and force carbon atoms to chemically bond with them, the resulting metal carbide molecules are physically larger than the original atomic structure.
Wait, larger?
Yes, they take up more physical space in the universe than the original metal matrix did.
So because the new molecules are literally bigger, the solid metal is physically swelling from the inside out.
Yes, and because it is swelling from within a rigid solid structure, it creates massive internal microscopic stresses.
The metal is fighting itself.
Exactly. The brittle glass-like carbides cannot handle that kind of internal stress, so they crack. The metal literally tears itself apart from the inside out due to this internal expansion.
That is insane.
That is why the data uses the specific word crumble. The internal structure is so destroyed by the volumetric swelling and the microscopic cracking that the steel just turns to a highly magnetic dust and chunks of brittle scale.
Okay, you just mentioned it being highly magnetic, and this is where my mind was totally blown by the source material.
Great field trick.
The data details qualitative field tests for carburization. It states that a change, specifically an increase in the level of ferromagnetism, can occur in some alloys. This means a magnet might suddenly stick to a normally non-magnetic tube.
Yes.
I want to paint a picture of what this means for the inspector out on the turnaround. So what does this all mean for the inspector on the ground? You could literally take a handheld magnet out of your pocket, walk up to a 300 series stainless steel tube, a material that is famous worldwide for being completely non-magnetic. And if you put the magnet against the pipe and it sticks with a loud clack, you instantly know the carbon has completely rewritten the internal crystal structure.
That is exactly what it means, and it is one of the most vital practical field detection paradoxes in the industry. Let us break down exactly why this happens.
Please do.
Austenitic stainless steels, like the 300 series, are non-magnetic because of that specific stacked orange, face-centered cubic crystal structure we talked about earlier.
Right, the tight packing.
That specific atomic arrangement is stabilized by elements like nickel and, crucially, by the chromium dissolved in the solid solution.
But remember what the invading carbon does. It diffuses in and specifically hunts down that chromium. It forcefully robs the matrix of the chromium to form those brittle chromium carbides.
Right. The carbon steals the stabilizing shield. When the chromium is severely depleted from the surrounding matrix, the local crystal structure of the iron can no longer maintain its specific face-centered cubic austenitic phase.
It shifts.
It becomes chemically unstable. The atoms literally rearrange themselves and physically transform into a ferritic or martensitic phase. And both ferrite and martensite are highly magnetic structures.
That is incredible. The invisible chemical theft of the chromium literally reveals itself through magnetism. So the degree to which that handheld magnet sticks to the pipe is actually a qualitative physical measurement of exactly how much chromium the matrix has lost to the invading carbon.
Yes. If it pulls slightly, you have early-stage depletion. If it snaps onto the pipe like it's a piece of plain carbon steel, you know the matrix is entirely compromised.
Wow.
But the data doesn't just rely on qualitative magnet tests. It details quantitative verification methods as well.
Because a magnet is just a yes or no kind of thing.
Right. Because while a magnet is a great field tool, it does not give you the full engineering picture. The text states that in a lab you will see substantial increases in hardness and a total loss in ductility.
Right.
And ultimately, it mandates that the true depth of carburization, exactly how deep the glass layer goes, must be confirmed by formal metallography.
Because field hardness testing and handheld magnets can really only tell you that the surface layer is damaged. They cannot tell you if that brittle glass layer is only a millimeter deep or if it has penetrated halfway through the wall.
Precisely. To know the true remaining strength of the tube, you have to physically extract a sample. You have to cut a piece of the tube out, take it to a lab, polish it to a mirror finish, etch the surface with highly specific acids, and look at it under a high-powered metallurgical microscope.
That sounds intense.
It is. Because only then, under massive magnification, can you actually see the dark, jagged network of brittle carbides penetrating through the grain boundaries of the wall thickness.
But taking a physical core sample out of a live, massive, high-pressure fired heater tube isn't exactly a routine Tuesday afternoon activity.
Not at all.
You have to shut the unit down, cut the pipe, weld in a new section, and x-ray the welds. It is a massive undertaking. So knowing how to find the crumbling magnetic metal with a lab microscope is great, but avoiding it entirely from the design phase is infinitely better.
Prevention is key.
That brings us to our final operational frontier: mitigation and prevention. How do the materials engineers stop this chemical invasion before it ever starts?
The data details the material selection limits. It states quite simply that engineers must select alloys with adequate resistance to carburization.
But as we established extensively earlier, almost all common structural alloys are susceptible if the heat and carbon conditions are extreme enough.
Which is a big challenge.
So what's the solution? The exact chemical defense mechanism relies on a very specific engineered barrier. Mitigation relies on selecting alloys that form stable oxides on their surface. This oxide layer acts as an absolute shield against carbon diffusion.
We touched on this briefly when we talked about why low oxygen environments are so dangerous. I want to explain exactly why these stable oxides prevent the carburization process.
Let's hear it.
We used the analogy of the chain link fence earlier. An oxide layer is essentially a highly controlled layer of good rust. But in this extreme high temperature context, we are talking about highly specialized, tightly adherent oxides like chromium oxide or aluminum oxide. These specific oxide molecules form a dense, completely continuous, impenetrable ceramic barrier right on the exact surface of the underlying metal.
So it's like a ceramic skin.
Yes. The molecular bonds holding this ceramic layer together are incredibly strong, and the atomic spacing is incredibly tight. The carbon atoms in the high-temperature gas phase simply cannot penetrate or diffuse through a continuous, stable oxide layer.
But here is a catch. The environment inside these roaring pyrolysis furnaces and cokers is so aggressive, the velocities are so high, and the temperatures are so extreme that standard chromium oxides often fail.
They just get blasted away.
They break down, they spell off, or they get chemically stripped away by the reducing gas flow, leaving the underlying metal naked again.
Which is why the data details a specific engineered solution for the most extreme environments. It mentions a specific engineered coating.
What's it called?
It says this protective benefit is commonly achieved by using a highly specialized alumina-forming coating, explicitly referred to in the industry as alanizing.
Alanizing. Okay, with alumina being aluminum oxide, how does alanizing actually work? Is it just like painting the inside of the tube?
Not at all. It is a far more robust, integral process. Alanizing is a proprietary thermochemical diffusion process.
So it's baked in.
Yes. Instead of waiting for carbon to diffuse into the steel in the refinery, the manufacturers intentionally diffuse pure aluminum into the surface of the steel in a controlled factory environment before the tube is ever installed. They bake the aluminum deep into the outer skin of the metal.
So they are essentially preloading the atomic lattice with aluminum.
Exactly. And when that heavily aluminum-rich surface is later exposed to the extreme heat of the refinery furnace, it instantly reacts to form a tough, continuous layer of aluminum oxide alumina.
Alumina is better than chromium oxide.
Alumina is exceptionally stable at extreme temperatures. It is vastly more stable and rugged than a standard chromium oxide layer. It provides a virtually impenetrable, permanent ceramic shield against the carbon gas, completely stopping the carburization mechanism dead in its tracks.
It's like pre-soaking our flexible sponge in a liquid armor that hardens into a force field, so that later on, it is physically impossible for the dirty water to ever soak in.
A very apt analogy. By heavily engineering the surface chemistry ahead of time to intentionally form that specific, ultra-stable aluminum oxide, you protect the highly susceptible iron and chromium-rich matrix underneath from ever even seeing the high-carbon environment.
It is brilliant engineering.
Yeah.
Okay, let's take a step back and look at the massive journey we have just been on. We have covered the fundamental atomic theory of carbon forcing its way into an expanding iron lattice.
We covered a lot.
We really did. We have run through the at-risk materials, from basic carbon steel all the way up to high-nickel alloy 800. We have decoded the environmental triggers, that critical 1100-degree threshold, and the absence of an oxygen shield.
And the inspection cues.
Yes, we visualized the terrifying reality of thick-lipped, brittle failures and internal crumbling. We've even walked through the sheer diagnostic magic of a non-magnetic pipe suddenly pulling a magnet out of your hand. And finally, we explored the engineered defenses of alumina coatings and alanizing.
It's a complex mechanism, but you have to respect it.
You absolutely do. I'm going to wrap up our substantive discussion by bringing the focus right back to you, the listener, whether you are in the control room, out on the unit, or designing the next major upgrade.
Consider the big picture.
Consider the incredibly delicate balance of your everyday refinery operations. Think about the massive hidden implications of what seem like standard operational moves.
Like the decoke cycles.
Exactly. The very steps you take to maintain thermal efficiency, like running a routine steam or air decoke cycle to burn the fouling out of a sluggish heater tube, can inadvertently be the exact trigger that permanently destroys that equipment.
It's a harsh reality.
By intentionally raising the temperature to burn off that surface coke, you might push the underlying atomic matrix of the metal just a few degrees over that critical 1100-degree Fahrenheit edge. In doing so, you throw the doors of the lattice wide open, and you initiate irreversible deep-wall carburization.
It happens fast.
It really challenges you to deeply rethink the hidden microscopic metallurgical costs of what we consider to be entirely routine maintenance procedures. Are you unknowingly sacrificing the long-term molecular structural integrity of your multi-million-dollar assets for a minor short-term gain in heat transfer? That is the kind of critical, invisible engineering problem that separates the truly elite operators from the rest. That wraps up our technical deep dive on this mechanism. Don't leave your exam or your asset integrity to chance. Head over to magintegrity.ca right now to subscribe to our full premium library, download the Visual Slide Companion Pack, and master API 571. Until next time, keep your assets safe and your inspections rigorous.